Hello, it's CMU Physics, and we will be learning about mechanical waves. So, first, we have to define what is a wave. So, in physics, a wave can be thought of as a disturbance or oscillation that travels through space-time accompanied by a transfer of energy. Examples of waves are ripples in a pond, seismic tremors, and musical sounds. Waves can occur whenever a system is disturbed from equilibrium position and when the disturbance can travel or propagate from one region of the system to another. And as the wave propagates, it carries energy. Now, there are two types of waves. We have mechanical waves and we also have electromagnetic waves. So, mechanical waves are waves that travel through a medium. So examples are sound waves, waves on a string, seismic waves, and water waves. We also have electromagnetic waves, wherein these waves can travel through empty space or where there is no medium. So examples are light, radio waves, infrared, and UV radiation. Now in this particular video, we will be learning more about mechanical waves. So as we know, mechanical wave is a disturbance that travels through a material or substance we call the medium. And there are three types of mechanical waves. We have transverse waves, longitudinal waves, and surface waves. Transverse waves, these are waves wherein the displacements of the particles of the medium are perpendicular or transverse to the direction of travel of the wave along the medium. Whereas longitudinal waves, the displacements of the particles of the medium are parallel to the direction of travel of the wave along the medium. And lastly, we have the surface waves, wherein these waves have both longitudinal and transverse components. So examples of surface waves are waves in the ocean. Now these waves have three things in common. So what are these things? First, in each case, the disturbance travels or propagates with a definite speed through the medium. Meaning to say, as the wave travels through the medium, the speed is constant. So this speed is called the speed of propagation or simply the wave speed, which is denoted by v. And its value is determined by the mechanical properties of the medium. Now you have to take note that the wave speed is not the same as the speed with which the particles move when they are disturbed by the wave. Another thing is that the medium itself does not travel through space. And lastly, in order to set any of these systems into motion, we must put in energy by doing mechanical work on the system. And you have to take note that waves transport energy but not matter. Now suppose a stretched string is shaken up and down just once. The result is a single wiggle or pulse that travels along the length of the string, such as this one. Note that when the pulse has passed, the string is restored into its straight line shape or in its equilibrium state. Now, if we give the free end of the string a repetitive or periodic motion, each particle in the medium will also undergo periodic motion as the wave propagates. And we have a periodic wave such as this one. So this is how we can make a periodic transverse wave. Consider a system with a mass which is connected to a spring that is moving in simple harmonic motion. The spring and the mass system is connected to a taut string. Now, as the mass and the spring undergo simple harmonic motion, the string will move also in such a way that it will result into symmetrical sequence of crests and troughs. Now, for periodic longitudinal wave, consider a long tube filled with a fluid with a piston at the left end. If we push the piston in, we compress the fluid near the piston, increasing the pressure in this region. This region of fluid then pushes against the neighboring region of fluid and so on, and a wave pulse moves along the tube. Now suppose we move the piston back and forth with simple harmonic motion. This motion forms regions in the fluid where the pressure and density are greater or less than the equilibrium values. So we will form regions with increased density and regions of reduced density. So for the periodic transverse wave, we can define the crest as the maximum displacement or the highest point of the wave pattern, and the trough as the minimum displacement or the lowest point of the wave pattern. And for the periodic longitudinal wave, we can define rarefaction as the region of reduced density and compression as the region of increased density. Periodic waves are easy to analyze and we can call them sinusoidal waves because it is sinusoidal in nature. So here we discuss the key properties of periodic waves. So we start with the amplitude, which is the maximum displacement of the particles of the medium with respect to its equilibrium position. It is denoted by the capital letter A, and it is given in meters. We also have the wavelength, which is denoted by the Greek letter lambda, and this is the length of one complete cycle. It is also given in meters. And then we also have the period, which is denoted by T. Now the period will tell us the time it takes to complete one wavelength. So it is given in seconds. Now we can also define the frequency of the wave, which is denoted by F. This is the number of waves passing through a given point per unit time. And it is given in hertz, which is equal to 1 over second. Now take note that the frequency is just equal to the reciprocal of the period t. And we also have the wave speed, which is denoted by v. And this is just equal to the product of the wavelength times the frequency. So hence, we can write v is equal to lambda times the frequency, which is also equal to lambda divided by t, the period, since frequency is just equal to 1 over t. So the wave speed is given in units of meters per second. Another property of a wave is the wave number, which is denoted by k. And this is just equal to 2 pi divided by the wavelength. This is given in radians per meter. And lastly, we have the angular frequency denoted by omega, which can be expressed as the product of the frequency and 2 pi, or omega is just equal to 2 pi times f. Now let us learn how to describe a wave mathematically. Many characteristics of a periodic wave can be described by using the concepts of wave speed, amplitude, period, frequency, and wavelength. Often, though, we need a more detailed description of the positions and motions of individual particles of the medium at particular times during wave propagation. If we are asked for the displacement of the particle of the medium, say for example, in a stretched string, We can only tell if we know which particle we're talking about. Therefore, the displacement of the particle of the medium with respect to the equilibrium position is dependent on the position x and also on the time t. That is, y is a function of x and t. Or we can just simply write y of xt. And we call this the wave function that describes the wave. When we know the wave function, this will allow us to know everything about the behavior of the spring at any time. So for example, take a look at this illustration. So we have here the graph of a sinusoidal wave which is propagating to the positive x-axis. Uh, this wave can be represented by or can be described mathematically as y of xt equals a sine kx minus omega t, where k is the wave number and omega is the angular frequency. Now, in general, we can describe a periodic wave mathematically using a sinusoidal function. So we have y of xt is equal to plus minus a sine kx minus plus omega t, or we can also express it as y of xt equals plus minus a cosine kx minus plus omega t. So the question is, when will the omega term be positive or negative? So in general, uh, when the wave is moving in the negative x direction, then we have a positive omega t term. And when the wave is moving in the positive x direction, then we have a negative omega t term. The next question is, when will the wave function be a sine or a cosine function? So take note that we have to know the displacement of the particles of the medium at time t equals 0 and at x equals 0. So for example, when the wave started at its maximum displacement at x equals 0 and at t equals 0, then we have a cosine function. And when y equals 0 at x equals 0 and t equals 0, then we have a sine function. For example, we have here a wave that is traveling in the positive x direction. And as you can see, at x equals 0 and at t equals 0, y is equal to 0. Therefore, the wave function of this wave is minus a sine kx minus omega t. Again, we have a minus omega t term because the wave is traveling towards the positive x-axis. Take note also of this wave here that is traveling towards the positive x-axis. Now, notice that at x equals 0 and at time t equals 0, the displacement of the particle is at its maximum. So y is equal to a at x equals 0 and at t equals 0. Therefore, the wave function of this wave is a cosine function, and in particular, we have here y of xt is equal to a cosine kx minus omega t. Okay, recall that the wave speed can be expressed by getting the product of the wavelength and the frequency. Now, recall also that we have the relationship of the wave number k to the wavelength. We have k is equal to 2 pi over lambda. And we also have this relationship. We have omega is equal to 2 pi f. Now we can actually relate the wave speed, the wave number, and omega. So from the first equation, we can get lambda. Lambda is equal to 2 pi over k. And from this equation, we can also get f equals omega over 2 pi. Now, if we substitute this value of lambda and f in terms of k and omega, we have here 2 pi over k multiplied by omega over 2 pi, then we will get this expression. So this expression, we can call it the phase speed. Now that we know how to describe a wave mathematically with the use of the wave function, we have y of xt. We can also easily get the particle velocity. We have v of xt as well as the acceleration. So, for example, we have a wave function that is denoted by this a sine kx minus omega t. So take note that this wave is moving in the positive x direction, and at x equals 0 and at time t equals 0, y is equal to 0. Hence, we have a sine function. Now, in order to get the velocity, we just have to take the partial derivative of y with respect to time. And for the acceleration, we just have to obtain the partial derivative of the velocity with respect to time. Or we can just write the second partial derivative of y of xt with respect to time. Our wave function, the partial derivative of this wave function with respect to time, so we have a multiplied by the derivative of sine kx minus omega t. So we have cosine kx minus omega t, and then we have the derivative of the phase, which is equal to minus omega. So we have here the velocity is negative omega a cosine kx minus omega t. Alright, and then for the acceleration, we just have to get the derivative, the partial derivative of v with respect to time. So we have the constants minus omega a multiplied by the derivative of the cosine function, which is, we have here minus sine kx minus omega t multiplied by the derivative of this term, which is minus omega. So hence we have you have a negative omega squared a, we have sine kx minus omega t, or we can simply write this as minus omega squared. So take note that this whole term here is just, yes, your y of xt. So this is your acceleration.